Hey everyone, let's go over problem 55 for precalculus. Let's read the question together. We have y, if y equals tangent sine pi x, the period of this function can be written as a positive integer n, determine the value of n, right? So I'm just going to write down y equals tangent, and we have sine pi x, great. And all I need to do is just to find out the period of this function. So how do I find it? Well, first, we use the same approach as we've done for problem 54 and problem 53. So step number one, okay? First, let's just try to sketch y equals sine pi x. Okay, so sine pi x would have been sketched just like this much. It would have been sketched like this, right? And that would be, this would be 2, this would be 1, that would be 1/2, and this would be 3/2. Okay, so we have all these shaped graph, and of course it's moving from 0 to 1 real quick, and like 1 to 0, and it falls down from 0 to -1, and -1 to 0, back again. This is going to be the sketch of y equals sine pi x. Now, step number 2. What will happen? Well, step number 2, we just need to find out y equals tangent sine pi x. Well, first, let's just try to investigate the small portion one at a time. If x is moving from 0 to 1/2, what do you know about y, or sine pi x? Well, I know that sine pi x, it's in fact moving from 0 to 1, but a little bit faster than the linear speed, okay? A little bit faster than the linear speed. All right, so that's going to be the linear speed, though I would say in my lecture or in the series, I usually say regular tempo. It's a bit faster than the usual speed of the linear functions. The linear function in this case would have been just y equals, would that be y equals sine, like y equals sine, y equals 2x, yes. Anyway. All right, so that's what's up, and I need to just perform tangent sine pi x. And this is going from tangent 0 all the way to tangent 1. And I told you that 1 is pretty much similar to, we have a very similar value as tangent pi over 3, which is roughly about root 3, okay? Roughly about root 3. Okay, so what do I know about tangent function? Well, tangent function, it's always going, always going in this particular directions. Tangent 0 to tangent 1 would be sketching this amount of curve, right? That amount of curve in between 0 to 1/2. So I got to actually perform step number 3. All right, so step number 3. Here we go. We have a graph that somehow looks like, the x and y axes. Ooh, this is going to be tough. There's going to be 0. There's going to be 1/2. Okay, so we have 1/2 out there. Check this out. If I were following the regular tempo, as it were from moving from, like 0 to 1/2, well, I would have sketched this amount of curve. I would have sketched this amount of curve, okay? That would have been the sketch of the curve, and of course, we started from tangent 0, I moved up all the way to tangent 1, right? So let me sketch that. Oh, that becomes tangent 1 out there. Okay, I'm going to say that, this particular value will be tangent 1, which is roughly about root 3. Pretty, like a little bit smaller than root 3, I would say. But hey, that would have been the regular tempo, but look at what has happened out there. Look at what has happened out there. If you see what's happening, well, it says it's spiking up faster. So if that's what's happening in the regular speed, we're actually speeding up in the very first few minutes or so for the first half, and we slow down. Okay, so we speed it up, and we slow down like this. We speed it up and slow down, and of course this shouldn't be like exactly the shape of the graph that it goes like this. It doesn't look like the concave up or concave down, but we definitely have something as spiking up, going a little bit faster, but somehow maintaining the same speed as its usual, and then slowing down, so it's dragging. Now, if you look at the line symmetry from 1 to 0, as x moves from 1/2 to 1, as x moves from 1/2 to 1, my y value starts to fall. My sine pi x was actually falling from 1 to 0. 1 to 0. So if it was falling from 1 to 0, I would have said that we should have sketched something about this amount of curve, because that would have been the sketch from tangent 1 all the way to tangent 1 all the way to tangent 0 using that sliding motion. But look at this. It dragged a little. The speed of the video got really slow, about 0.25, the usual speed, and then it's going faster, right? So it doesn't drag that much. It doesn't fall that much, but it's speeded up and it falls down. All right, it got to be, in fact, let me erase this part. Oopsie. Yes, let me erase this part. Let me show you a better picture. It fasted up and going and then drag down a little. Yes. So that would have been the sketch of this function. It looks like somehow bell curve, and we got to follow the same trail back again as using the point symmetry. I would say you can have the point symmetry in this direction from 1 to 0, 0 to 1, 0 to -1. So if I sketch from 1 to 3/2, 3/2, well, it was falling with the regular tempo, and if I follow the regular tempo, well, the regular tempo would have fall from tangent 0 to tangent -1. So tangent 0 to tangent -1 would have been actually falling it down like this. But it doesn't go this way. It has to fall pretty much faster than usual, and it dragged little, okay? It dragged little, and then we have to follow up the same trail like this. Okay, so that will be the sketch of this function from 0 to 2. Now, there wasn't any, the adjacent max or adjacent min, so I would say this becomes one full period, right? That becomes one full period, and you can check that this one full period will be reiterated once more, and the distance between 0 to 2 will be just one full-size bundle of this periodic function. So I would say the answer for this question, the period, would have been 2, and that shall be it.